Alright, so I'm going to teach you the integration technique known as integration by substitution, also known as U-substitution. So we created this technique, or more like discovered it really in the math, that to make up for the absence of a chain rule in integration. So if we wanted to, say, differentiate some functions, call it 2x minus 1 to the 1/2, well, that'd be easy. We'd be a function within a function. We use the chain rule. So the derivative of the inner function, which is just 2, times the derivative of our outer function, which is 1/2, times our inner function, 2x minus 1, raised to 1 less than our old exponent, so it becomes negative 1/2. So 2 times 1/2, that cancels. So our derivative is now 2x minus 1 to the negative 1/2. Pretty simple. Now, say we wanted to do the reverse. Say we wanted to antidifferentiate 2x minus 1 to the 1/2 with respect to x. We would have to do what's called a U-substitution. So we take some variable to equal our inner function. So, well, what are we going to do? So we'll take some variable u to equal our inner expression, 2x minus 1. We just use u just because it's traditional, hence the name U-substitution. So if u equals 2x minus 1, well, we can just replace this 2x minus 1 here with a u. So instead of 2x minus 1 to the 1/2, it's u to the 1/2. Now, this former integrand is in terms of x, so we have a dx. Now, we can't just integrate u with respect to x, because wait a minute, there's no x. So instead, we need to find some relationship between dx and du. So how do we do that? Well, let's take the derivative of our original relationship that we stated. So the derivative of u, that's du, and the derivative of 2x minus 1, well, that's just 2 dx. Well, wait a minute. So we know that du is twice dx, so let's divide by 2. We know that 1/2 du equals dx. So now, wherever we have dx up here, we can just replace it with 1/2 du. So here's our du, and 1/2, that's a constant multiple, so let's just put it outside. So we have 1/2 du. So now, this is really easy. The 1/2, the integral of u to the 1/2 du. Well, power rule. So we'll have 1/2, add 1 to our exponent, so it becomes u to the 3/2, then divide by our new exponents, which is 3/2. So let's just multiply by our reciprocal of our new exponent. So we'll have 2/3. And then, of course, plus our constant of integration. So we have a 2 on the bottom, 2 on the top. Let's cancel those. So we have u to the 3/2 over 3 plus c. Pretty simple. Except now our answer is in terms of u. We want it to be in terms of x. So we just back substitute 2x minus 1 for all our u's. So we'll have 2x minus 1 to the, say, 3/2 over 3 plus c. Problem solved. Now, let's try a little more complicated problem so I can introduce you to another cool idea. And then also, let's try to do definite integration, which is a little bit different. So our definite, let's try take the definite integral from, let's say, 2 to 4 of x times the square root of x squared minus 1 dx. So, okay, saying what are we going to make our u equal to? Well, let's make it equal to x squared minus 1. So u equals x squared minus 1. So we know that this is going to be u. What about our x? And what about our dx. Well, let's try substitute for our dx first. So we'll take the derivative of both sides of our stated relation. So derivative of u is du. Derivative of x squared minus 1, well, it's just 2x dx. Now, wait a minute. We can't just solve for dx and plug it in, because then we'll get du over 2x equals dx, and then again we'll have an integrand in terms of x's and u's, which is not unified and difficult to do, or actually it's impossible to do. So instead, we need to find the function parts of our dx side of this relation and try find those in our integrand. Well, wait a minute, the function part here is x dx. So do we have an x dx in here? Why, yes we do. Right here, x dx. Let's rewrite this for clarity from 2 to 4. X squared minus 1 times x times dx. So here's our x dx. So let's take this and solve for x dx. Well, that's just a matter of divide both sides by 2. So 1/2 du equals x dx. So our new integral is going to go from 2 to 4 of the square root of u du. Hey, that's pretty simple. Now wait, here's the kink when you do definite integration. When we originally took the definite integral of x, what it really should have looked like is x equals 2 and x equals 4. So our limits are x equals 2, x equals 4. Our integrand is x times the square root of x squared minus 1 times dx. Now in here, everything is in terms of x. Our limits, our integrand, and our dummy variable. Now in here, our dummy variables in terms of u, our integrands in terms of u, but here our limits are still in terms of x. So what we need to do is we need to turn these into limits in terms of u. So what do? We plug in these limits into our stated relation and between u and x, and then replace those. So instead of x equals 2 and x equals 4, we'll have u equals something and u equals something else. And instead of u to the square root of u, let's just say u to the 1/2, and then du, and then, wait a minute, this is 1/2 du, so this will be 1/2 du, 1/2 du, or sorry, this is not, so 1/2 du. So here we have our 1/2 du equals x dx. 1/2 du equals x dx. U to the 1/2, well, that's x squared to the minus 1 to the 1/2. And now we just got to take care of our limits. So if our state relation says u equals x squared minus 1 and x equals 4, we'll have 4 squared minus 1, which means we'll have 16 minus 1, which will be 15. So our upper limit's going to be 15. And our lower limits, that's going to be u equals 2 squared minus 1, which will be 4 minus 1, which will be 3. So u equals 3. So now, instead of integrating from 2 to 4, x times the square root of x squared minus 1 with respect to x, it's an equivalent thing to say that 1/2 of the square of, 1/2 of the integral from 3 to 15 of u to the 1/2 du. So this is easy. So I'll have 1/2 integral. Let's say, now, well, we kind of just did that one, so we add 1 to our exponent, so we'll get 3/2 and divide by our new exponent, or we could just multiply by the reciprocal, so we'll get 2/3. And we'll take that from 3 to 15. And since it's definite integration, we don't have to worry about our constant of integration, right? So, well, let's clean this up. Well, we have 1/2 times 2, so we can get rid of those. So we have u to the 3/2 over 3. Okay? So, taken from 3 to 15. So u to the 3/2, that's the same thing as square root of u cubed all over 3. So we're going to take that from 3 to 15. So we're going to take that from 3 to 15. So we'll plug in our 15. So we'll take 2, the square root of 15 cubed over 3, and minus that from the square root of 3 cubed minus 3. So the square root of 15 cubed, that's 15 square root of 15, right? Over 3 minus 3 square root of 3 over 3. And we can simplify that. We have 3 on top, 3 on bottom. We have 3 on bottom, we have a 3 on top, but it's 3 times 5, so there's going to be a 5 left over. So this is going to look like, in the end, 5 square root of 15 minus square root of 3. And that is the definite integral of our original function up here.
I'm Stuart Jeffries. I'm a professor in physics and astronomy at the University of Hawaii, and I'm associate director here at the Institute for Astronomy on Maui. What I do is I'm a researcher, and I research into solar physics and also imaging.
Are there any other topics from the list that I showed you that I kind of went over in my videos that look especially important in your work or any of the work you do outside of your occupation?
Okay, as I said, optimization is very big for me. I do a lot of problems where I have to optimize different functions. That requires differentiation. I use the mean value theorem in a lot of work. And just to look at your list again. Actually, out of the 20 items you have on here, probably more than half of them I use during doing my scientific research. So I mean, I'd be lost without math.